Hi and welcome back to Podcast School. This is another AS Technology and Design video podcast, and today we're going to be taking a look at binary. Okay, have a look on the screen. There is a signal, an analog signal. It's moving continuously in time from left to right. Okay, and it has varying amplitude. Amplitude being the vertical distance between the x-axis and anywhere on the graph. Okay, but vertically, not at an angle, vertically. So that's amplitude. And this is an analog signal because, as I said, it's continuous. Let's have a look at now a digital signal. So let's get our old graph back again, and you can see the difference. Right, so there's the old graph, just as before, but this time I'm going to split the area under the graph with some dashed lines, and I'm going to give each dashed line a value from 0 through to 20. Now what I'm going to do is I'm going to approximate area under the graph. I'm going to, in other words, find a point on the graph which best matches the closest dashed line. Okay, so let's take a look over here. The graph passed this point at about 10, so I've estimated, sorry, about 11, so I've estimated that point to be about 11. And again, well, it's obviously risen a bit, but I decided that in the middle of this bar it was still closest to 11. The next bar, well, I reckoned that it was obviously closer to 13 there, okay, and the next one closer to 15, but the one beside it, it hadn't moved sufficiently enough to say that it was 16, so I kept it at 15, and so on. Okay, so what I've done is I've split the graph up into portions, and I've estimated where the graph is in relation to the y-axis. Okay, and I've come up with these bars. Now, I've also given you the definition of the word discrete and the word quantized. Discrete meaning just it's something being separate or distinct, and quantized meaning something that's been restricted to a prescribed set of values. In other words, something that's been approximated. So we can say that a digital signal is both discrete and quantized. Okay, so that gives you sort of where this signal is going to come from, but we're going to build upon it now, and I'm going to show you exactly what the digital signal will become. Okay, so let's move on. I'll show you where that comes from. So this is really getting toward the problem now. I've got a situation where I have to be able to transmit this signal digitally. So how might we do it? Okay, well, we could use the values on the left here, and we could read these off. So I've noted these down for you. Okay, 11, 11, 13, 14, 14, 15, so on. Right down through till we get back to 10. This is an approximation of the analog signal in decimal values. Okay, now pretend for a second that this analog signal was actually a sound wave. It had been produced by a microphone. We might want to record that digitally and put it on our MP3 players, perhaps just send it across the internet or store it on a hard drive. We need to be able to store it digitally. This is the first step. We need to quantize first of all and get a set of values. But how do we store these values or even transmit them? Well, this is how it's done. These are the values again, and I've said here that we have to be able to send these values. We might need to transmit them electrically, okay, across the internet. And the title of this lesson, binary, is where or how we do this. Okay, let's have a look. You know that a digital signal can either be just on or off, a 0 or a 1, a low or a high. There's nowhere else a digital signal can be. Unlike an analog signal, which can take up any state in an infinite amount of values. But in digital signals, we only have 2 values. Okay, so that's just a little bit of revision. So why am I telling you that then? Well, let's have a look. you've heard of bits before, bits on a computer and bytes. There's 8 bits to every byte, okay? This is where this comes from, and I think sometimes it's just easier to show you all this at once and then review it. So we have an 8-bit number here, starting on the right hand side, strangely enough, and moving to the left where we have our most significant bit. And if that's the most significant bit, you realise that LSB must be the least significant bit. Next we're going to put in another row where we take 2 and we take it to the power of, and then the bit number. So 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and so on. Which would give us a decimal value of 1, 2, 4, 8, 16, 32, 64, and 128. Okay, now where did that come from, or why am I telling you that? It will soon become clear. Really, the whole point of this is, if we use the numbers in pink, we can make any number by adding them to give us, or we can add any number of these to give us any number that we so desire. So let's take our old example that we had earlier, 11, 11, 13, 14. Here we go. So there is our bit number. That's our binary equivalent and our decimal value of that. So you've seen where that comes from. Now look, how could we make 11 from these pink numbers? Well, if we use an 8 and a 2, that gives us 10, plus a 1, that's 11, of course. 13, an 8, a 4, a 1, gives us 13. 14, yeah, 8, 4 and 2. 15, 8, 4, 2 and 1. And look, we can represent these values now with either a 0 or a 1. In other words, we can represent these values digitally. And I'll continue the table. We can create any value here just by using these binary numbers. So brilliant, we've got it. We can now transmit numbers, any number, digitally with either just a 1 or a 0 using 8 bits per number. Okay, so for every number we must transmit 8 bits or 1 byte. And here's just one last example. So this number 10, sorry, we'll start over here, 00, 00, 10, 11 will be transmitted like this. Nothing, 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 so nothing will be transmitted. Then a 1, then a 0, then a 1, and then a 1. Alright, and that will be 1 byte transmitted in order to transmit that one word. And then we just start with the next number and we transmit it the same way and the same way and the same way until we have all those numbers that we had earlier transmitted, and we have actually transmitted that analog signal, albeit approximized, but still it'll still sound pretty good. And as you know, your MP3s that you listen to on your iPod or whatever sound pretty good, and you would not know that they're actually only approximations to the real thing. Okay, so that's it for now. I shall leave you at this point. If you have any questions, you remember you can email me at info@podcastschool.net. And as I always try and remind you, pick up the notes that are in PDF format, because they're much higher quality, and you can see the figures and some of the words so much better. So make sure you pick those up. Okay, until next time then, bye bye.